Hello everyone, welcome to the class once again. I hope you're all doing good and you're practicing problems of each chapter. The last class we have studied about the transmission of heat through conduction and convection, and we started understanding the concept of radiation. I told you that radiations are nothing but it's all are electromagnetic waves. Now electromagnetic waves generally travel in straight lines. They are just like light waves. So they will show all the properties of a light wave. Let's go ahead and let's understand the concept of radiation. Now see, first of all, any body at any given temperature is going to emit radiation in all directions. That means whatever object you are seeing near you, that is actually emitting radiation. If I take an example, see, this is a duster. It is going to emit radiation in all the directions from it. Similarly, radiations are falling on your body, on any other object from everywhere in the atmosphere, in the environment. Radiations are also falling on this object. Let's go ahead. So here we have radiations are being emitted from this object in all directions. So I am going to draw the depicting how the radiations are being radiated from the object, and it's radiated in all the directions. Now I also told you radiations are also incident on the object from all directions. It's also incident on the object from all directions. Now there's a law called Stephen's law, and we have Stephen's law says that actually radiations emitted by an object can be described with a with a different formula that is given as, here we have, suppose we have any object that is radiating and rate of emission of radiation energy, that is power of the radiation, that is given as for any body, that is E sigma A T to the power 4. That is, we can write this equation as power P emitted, that is rate of heat energy emitted per unit time, that is equal to E sigma A T to the power 4. T is the temperature of the body. The body has a temperature, that is T of the body, temperature T. E sigma A T to the power 4. What is E here? The term E we have here used. This E is known as emissivity. This E is known as emissivity. It has a value which lies between 0 to 1. The emissivity lies between 0 to 1 for any body. Now this term, once again we have used here sigma. Sigma is Stephen's constant. It's also known as Stephen's-Boltzmann constant. It's Stephen's constant. Its value is also fixed, that is sigma is equal to 5.67 into 10 to power minus 8 with proper units. Now how to check the units? You see here, the unit of power will be watt, the unit of area will be meter square, the unit of temperature power 4 will be Kelvin power 4. So unit will be watt per meter square per Kelvin power 4. Now emissivity has got no unit. It is unitless. Need not to worry about that. It is only describing us that what is the amount of energy that will be radiated out by the given object. So this was all about the Stephen's law, and in this law we only come to know about the rate at which the energy is radiated by the body. Let's go ahead. This was all about radiation through a body. There are certain terms that we should know earlier. At the first go, there are certain terms. Those are absorptive power. Those are absorptive power. Now, what is absorptive power? Now, any body, it is going to absorb some amount of radiation that will be incident on it. Now, suppose on a body, 80 units of radiations are incident on it, and compared to the 80 units of radiation, it is absorbed only 60 units of it, and 20 units is not absorbed by the body. So the ratio of the energy incident with the ratio of the energy absorbed with respect to the energy incident, that is the absorptive power. The ratio of energy incident to energy absorbed, This is known as the absorptive power of the body. The ratio of energy incident to the energy, sorry, the ratio of energy absorbed, not incident, the ratio of energy absorbed, because that is going to be less. The ratio of energy absorbed to the energy incident on the body, this is known as absorptive power. The ratio of energy absorbed to the energy incident is absorptive power. Now, how to give the value? It is represented, it is actually represented by using letter A. This is a ratio energy absorbed divided by energy incident. So, we are going to have this energy absorbed divided by energy incident. This will give us the value of absorptive power. First thing that you should know, whatever energy is incident on an object, note that value divided by the total energy incident. So, whatever energy is absorbed divided by total energy incident, that will give you the absorptive power. Next one, we have the next term, that is emissive power. Emissive power is a very simple term. This is actually the rate at which energy is emitted by the body per unit area. The emissive power is the rate of energy emitted per unit area, the rate of energy emitted by the body per unit area. This is known as, now don't confuse it with emissivity. The rate of energy emitted by a body per unit area is emissive power. Per unit area is emissive power. So, very simple, we have got emissive power will have a unit. So, let me write down. First of all, emissive power is the rate of energy emitted per unit area. So, power divided by area. So, it will be watt per meter square. This will be the unit of the emissive power. Don't confuse it with emissivity, first thing. So, what do you do? Take note till here. I will start from the other end by rubbing the other part. Now, I believe that you would have understood the concept of emissive power and absorptive power too. Now, these are some basic concepts which will be used in coming sections. Now, let me go ahead with the next one and let me tell you about black body. Now, what is a black body? Black body is such a body which is going to absorb all the radiation incident on it. If it is going to absorb all the radiation energy incident on it, its absorptive power is going to be 1, because it's going to absorb all the energy incident on it. So, black body, it absorbs all the energy incident on it. Absorbs all the energy incident on it. Such a body is known as black body. Now, for black body, I told you the rate of heat energy emitted by a body is given as P equals to EA sigma A to the power T power 4. Now, we know just now P equals to EA sigma T to the power 4. Now, this is for radiation. Let me tell you, black body is also a perfect radiator. It will radiate with the maximum at a given temperature compared to any other body. So, for black body, we have emissivity E is equal to 1. For black body, we have E equals to 1. So, we have for black body, P will come out to be A sigma T to the power 4. We will get this because E equals to 1 for a black body. Now, let me tell you, a black body will be normal if you take a lamp black that can behave nearly to a black body. It is very difficult to obtain a perfect black body, but we can try to construct a black body as per the given diagram. If you construct an arrangement, what do? You construct a box which has a very narrow opening. You construct a box which has a very narrow opening as shown. Now, let's say if any energy is incident on it, it gets reflected. Let me draw it completely. Yeah, now it's okay. Now if any energy by any source, if it is incident here in the black body, what will happen? Multiple reflections is going to take place, and then we are going to have the light or the electromagnetic wave will be trapped within this. It's not going to escape out of it. This is one method to make a perfect black body. That is, you construct an arrangement and you see how it can be made. This is how we have made a perfect black body, because we find that through this narrow opening, the light energy, whatever will be coming out, it will be through multiple reflections, it will be remaining inside and it will not be able to escape outside. So this is how we can make a perfect black body. Now see, this inner part is actually made reflecting so that all the light energy remains in. Or you can say that inner body is actually perfectly black, so hence whatever light is actually radiated also, that remains inside. So we are going to make nearly a black body. Next thing, let's go ahead and let's understand Kirchhoffs law. Very simple law, Kirchhoffs law. Now in the chapter of radiation, in the concept of radiation, what is Kirchhoffs law? Don't confuse it with the Kirchhoffs law of electric current or Kirchhoffs law used in the concept of capacitance, that we'll be seeing later on. But let me tell you about the Kirchhoffs law used in the radiation. First of all, it says that the ratio of emissive power to the absorptive power is same for every body. The ratio of emissive power to absorptive power is same for every body at a given temperature, and that is equal to emissive power of black body. The ratio of emissive power to absorptive power is same, absorptive power is same for all bodies at a given temperature. For all bodies at a given temperature. Now how to write it? Now we know that for a black body the absorptive power is given as 1. So if I write emissive power, if I write for one body as E1 by A1, the ratio, this will be equal to E2 by A2. For another body, this will be equal to E by A. This is what we are referring to black body, because black body is also a body, so you can write in this way, E by A of a black body. So this is the ratio that is actually signifying the Kirchhoffs law. I will talk more about it. What you do first, take note till here. I will start from the other end. Okay, I believe that you would have understood about Kirchhoffs law. Now I told you for black body the absorptive power is A equals to 1. So we can write E1 by A1 is equal to E, where A equals to 1 for black body. So I am using this as E, where E is the emissive power for black body. Because A is equal to 1 for black body, so hence I am using E equals to emissive power of a perfect black body. Now this is all about Kirchhoffs law. E by A is constant for all the objects at a given temperature. Now we know the energy that is radiated by your body, that is dependent on the temperature and that is dependent on fourth power of the temperature. Let's go ahead, let's try to see how a body gets cooled down gradually. So let's go ahead and let's learn about cooling of a body. Now we know that if the temperature of a body is, let's say, T naught, if T naught is the temperature of the body, we have a body, its temperature is, let's say, T naught. So what is going to happen? Radiations are going to be radiated from this body. The rate of losing the heat energy, now see, rate of loss of energy by the body We know that that is given as P1, that will be EA. No, see, let's go with any body we have taken. So that will be EA sigma T to the power 4. We know this. This is what the rate at which it is going to lose the heat energy, T naught power 4. Now, from all other sources, if the room temperature is, let's say, Tc, the room temperature, let's say Tc, so it's going to also receive energy that is incident on it. So rate of gain of energy, that will be P2, that will be given as A sigma Tc power 4. This is how the rate of energy that will be gained by the body. Now see, during equilibrium what will happen? T naught will become equal to Tc, because gradually it will acquire the room temperature of the body. So T naught will be equal to Tc. So let me write down, at equilibrium you will find that T naught is equal to Tc, or we can write P1 is equal to P2, because the rate of energy radiated will be equal to rate of energy incident on the body. The temperature is uniform as per the room temperature. So E sigma A T to the power 4 will be equal to, and since T naught is Tc, so that we can cancel out later on, A sigma A Tc power 4, this and this are equal, so we can write E is equal to A, or A equals to E. A term we have used for the absorption of the radiation that is incident on the body. We find that the A that we have used, that is equal to emissivity of the body. Now let's say the temperature is different. So if I write down an equation which will give me with what rate the body gets cooled down. You see, rate of loss of energy, net rate of loss of energy will be what? Because energy is radiated also, energy is incident also. That will be given as P is equal to P1 minus P2. So we can write E sigma A T naught to the power 4 minus Tc to the power 4. Whenever the equilibrium is not attained, this will be the rate of loss of energy. P is what? dq by dt. Rate of loss of energy dq by dt is equal to E sigma A T naught power 4 minus Tc power 4. With this rate is going to lose energy. Now dq by dt, or first we know that the small heat energy that is transmitted, that is given as mass into specific heat capacity into change in temperature dt divided by dt. mc dt by dt is equal to E sigma A T naught power 4 minus Tc power 4 minus Tc power 4. This is what we have obtained here. So we got this, mc dt by dt equal to E sigma A T naught power 4 minus Tc power 4. Now with this rate it is getting cooled down, and we have written dq in terms of this. So rate of change of temperature, if you see, let me rub this part. Rate of change of temperature, it's cooling down, so dt, this will be negative, okay, it's cooling down. So to make it positive, I'm actually multiplying a minus sign here. So this will come out to be E sigma A divided by mass into specific heat and into T naught power 4 minus Tc power 4. I believe that you are simultaneously noting down each of my step. Remember this formula, this is rate of decrease in temperature of the body. Why I have used minus sign? Because dt will be negative. The temperature is going to be in the negative direction. It's decreasing, so that's why I have used a minus sign here. Now, if the temperature difference between the temperature of body and the surrounding is very small, how can we reach on to a very simple formula that is given by Newton's law of cooling? Newton's law of cooling. What Newton's law of cooling states us? If the difference in temperature of the body and the surrounding is small, that is, if I write T naught is equal to Tc plus delta T. There is a very small difference between T naught and Tc plus delta T. So if I write T naught power 4, that can be written as Tc plus delta T power 4, not a big thing. Now we can take Tc outside, so Tc power 4 will come out, and here we are going to get delta T by Tc power 4. Not a big problem. Now from binomial expression, we know that this term will be very small. Delta T is already very small, so delta T by Tc will be very small compared to 1. So we can use binomial expression. So we can write this is Tc power 4, 1 plus 4 delta T divided by Tc. This is what we are going to obtain. This is T naught power 4. Multiply Tc power 4 inside. So you are going to obtain, if I multiply Tc power 4, so we will be having T naught power 4 is equal to Tc power 4 plus 4 delta T. You see here 4 Tc whole cube delta T plus 4 Tc whole cube delta T. This is what you are going to obtain. 4 Tc power 3, because 1 Tc will be cancelled out, delta T. So we got T naught power 4. Take the Tc power 4 here, you will be having T naught power 4 minus Tc power 4 is equal to 4 Tc whole cube delta T. Obtained. We got this formula. Just now you see here, the rate of decrease in temperature minus dt by dt dc was given in this way. T naught power 4 minus Tc power 4 we have written, that is 4 Tc whole cube delta T. Now T naught power 4 minus Tc power 4 is proportional to delta T. T naught power 4 minus Tc power 4, Tc remember that is the room temperature, that comes out to be proportional to delta T. Here you see all terms are constant, E, sigma, m, c all are constant. We have this term. What we can write? We can write minus dt by dt is equal to a new constant we can apply here, and that will come out to be minus b. Let me write down here only b delta T. This is what we are going to get, because I have replaced T power 4 minus Tc power 4 by, because it's proportional to delta T, so we can replace that with delta T here, and if the temperature difference is small, so we can replace entire this as constant with a single term, that is B delta T. What is this delta T? This delta T is the difference in temperature of the body and the surrounding, a small difference in temperature. So we can write the rate of cooling of a body is directly proportional to the difference in temperature of the body and the surrounding. So if I write down that the rate of cooling is directly proportional to the difference in temperature of the body with the surrounding. This is what Newton's law of cooling says. That now see, I have used here minus sign that depicts that the body is losing temperature, it's cooling down. So this was all about Newton's law of cooling. What we did, we saw that the difference in temperature of the body and the surrounding is quite small. So we started with this. We saw that how we can come to T power 4 minus Tc power 4. We obtained that it reached to me and gave us the result that is proportional to the difference in temperature of the body and surrounding. Substituted in the actual formula, so we got this. So Newton's law of cooling also says the same thing. The rate of cooling of a body, that is decrease in temperature with time, that is proportional to the difference in temperature of the body and surrounding. So we got here, and the final formula comes out to be minus dt by dt equals to b into delta T. This is what you can use. Let's go ahead. After Newton's law of cooling, one more part we are left with, that is VN's displacement law. The next part is VN's Displacement Law. In this, the thing that we should know, VN's displacement law, in this what happens. Now for any body, for a black body, if I plot a curve between the rate of emission of energy with respect to the temperature of the body and with respect to the wavelengths of the electromagnetic radiation that has been emitted, if I draw it, I'll find a relation. You see here I am going to plot a curve for several lambda, and for given the rate of energy that has been radiated. Now for given temperatures, I will find that it will follow a different curve. This is what is the equation looks like. Sorry, the graph looks like. This temperature, let's say it's T1 2000 Kelvin. Let's say T2 we have 3000 Kelvin. T3 we have 4000 Kelvin. Now see the minimum value of the lambda. This peak shows me the highest value of the radiation energy that is emitted for a particular value of lambda. You see here, the peak is actually going with lesser value of lambda, that is energy is more for such lambda. Now if I take this as the lambda minimum for anyone, this lambda minimum multiplied with the temperature, that will give us a constant that is known as VN's displacement law. So we got this, lambda m into T is equal to B. Now here B that I have used, this is the VN's constant. This has got a value. Now let me give you the value of the VN's constant, that is 2.898 meter Kelvin. You can see here the lambda will be, unit will be meter, temperature will be in Kelvin, so 2.898 meter Kelvin, that is the unit of the constant that has been used here. This equation is known as VN's displacement law. So what you do, take note till here. I will start from the other end, take note till here. Now just make one change here, it's 2.898 into 10 to power minus 3 meter Kelvin, then only it will be complete in its value. Now this equation is known as the VN's displacement law. The lambda that we are using, that is for the minimum value of lambda, that is the maximum energy that is having. Now for that, the maximum rate at which it is radiated, it's plotted here for lambda and for given temperatures. We are finding that the minimum value of lambda is inversely proportional to temperature. So we can write lambda into T equals to a constant B, that B is the VN's constant. Its value is 2.898 into 10 to the power minus 3 meter Kelvin. So here I am writing one more thing, lambda m is inversely proportional to the temperature of the body. This was all about VN's displacement law. So after learning all this, we can start practicing questions. Questions will be taken up in coming classes, but you all start practicing questions and you all will be finding that it will be easy now for you all to solve such thing. I believe you all can do it. So in today's class, what we studied about radiation. We saw what is black body. We saw what is the equation, what is the Stephen's law, that provides us with the equation which will entail us to find out what is the rate of energy emitted by your body. And that is E sigma A T to the power 4, that is proportional to the fourth power of the body. We saw what is absorptive power, we saw what is emissive power, we saw what is Kirchhoffs law. Now, after this, we saw the cooling of a body. We saw that cooling of a body was proportional to fourth power of the temperature of body minus fourth power temperature of the surrounding. Then we saw Newton's law of cooling. The difference in temperature of the body and the surrounding is small, we can say that the rate of loss of temperature or the rate of cooling of the body is proportional to the difference in temperature of the body and the surrounding. The last one that we have seen, that is VN's displacement law. It says that for at any particular temperature, if you plot a curve between the rate of energy emitted with respect to the wavelength of the radiation, we can write that the wavelength, the minimum wavelength, that is for the maximum power, that will be inversely proportional to the temperature. That is, lower the temperature, maximum is the wavelength. That means minimum is the value of energy. Now, and for high temperatures, higher will be the value of energy. Now you can see that the equation says that lambda m into T equals to B. That is the equation for VN's displacement law. B is VN's constant, that is 2.898 in 10 to the power minus 3 meter Kelvin. Go ahead, solve question, find it easy and simple for you all. I wish you all the very best. I'll meet you all in the next class. Till the time, thank you everyone.